Hey class, here we have this fun problem number 48, and a few of you have been asking me about it and wanting a few pointers, so I thought I'd go ahead and help you out. So we're told that we have a wire and we have a pipe. We have current going through the pipe, entering into the page as implied by the picture, and we're asked to figure out what the current is in the wire, and in figuring out the current in the wire we need to determine it based on knowing that there is a certain ratio of magnetic fields at point P, which is labeled for us, and at point C, or at least that's what I'm going to call it, the center of the pipe here. And we're told that that ratio is 1.03, but opposite directions. So I'm going to create an equation for that. I'm going to go ahead and call my ratio, I don't know, we can give it any letter we'd like. I'm going to go ahead and give it the letter X, why not? Okay, and so what that means is that our field at point C times that ratio, whoop, I almost wrote 1.03, that's the ratio in this problem here, but it's X, is going to be equal to the opposite direction of BP. Okay, so in order to figure that out, we need to figure out what BC and BP are. And so really what we're going to have is that the B for either of these, whether it's C or P, I'm going to start with C, is going to be equal to the B field due to the wire at point C plus the B field due to the pipe at that point, in this case point C. So in order to figure this out, we need to pick a direction we think the current might be flowing through the wire. We don't know, right? That's one of the things we're asked to, what is the direction of the current? But we have to pick a direction initially, and then we will figure out if we're right or wrong based on the solution that we get when we go to solve. So I'm going to go ahead and say, alright, I'm going to pick into the page. So my current here for this wire is going into the page. So what that means is, by the right-hand rule, the field produced at point C is going to be this way. So that's the B due to the wire at point C. I'm going to rewrite that so you can actually maybe tell what it is. So that's the B due to the wire at point C. And the B field due to the pipe at point C, since it's at the center with uniform charge distribution, is actually going to be 0. So that's 0. And so all we're left with is the B field due to the wire at point C. As you can notice in the image, or as you can see, it's in the negative direction. So I'm going to go ahead and write out the equation for it. It's in the negative direction, and we quantify the B field due to a wire at some distance away. In this case, our distance is 3r. It's going to be equal to a negative mu naught times I in the wire, all divided by 2 pi r, and in this case our r is actually 3 times this variable r, since that's the distance we are away. So that's the B field at point C. Okay, what about the B field at point P? Well, again, it's going to be the sum of our two B fields. Again, using our right-hand rule, we can see that the B field due to the wire at point P is going to be in this direction. So we got the B field due to the wire at point P plus the B field due to the pipe at point P, and that's going to be in the opposite direction. Right? Again, using our right-hand rule with the current, so I'm going to make sure to include a negative sign in front of my B due to the wire since it's in the opposite direction. And again, we use the same equation, the same relationship that we derived in class, both using the Biot-Savart law and Ampere's law. We derived it. Alright, we found that for the wire, we're going to have negative mu naught I of the wire over 2 pi times the distance away, which in this case is just a single r, this distance here, and then plus the B due to the pipe, which again is going to be mu naught times the current, which now is I sub P, the current in the pipe, alright, which is given to us, divided by 2 pi times its distance away, and the distance that the center of the pipe is away is going to be 2 times r. Okay, so now we can put these together with our relationship that we have up here. Alright, so I'm going to scroll down just a little bit, zoom out so we can see everything. So what we have is BC, so we have negative mu naught I of the wire over, I'm going to just multiply this, it looks like we got 6 pi, no, just kidding, I'm not going to multiply, because my 2 pi's will cancel, so 2 pi times 3r multiplied by my ratio x is going to be equal to a negative of my BP, so the negative sign I'm going to go ahead and distribute, so distributing that gives me a positive mu naught IW over 2 pi r minus, again distributing that negative sign that we had in our relationship here, minus this whole term, which is mu naught I in the pipe divided by 2 pi times 2r. Cool, so now we can go ahead and see what will cancel out for us here. So we can see everything has a mu naught in it, so we can cancel that. Everything has a 2 pi, cancel that. Everything has an r, cancel that. Oh man, this is getting nice real quick, okay? So I'm going to scroll down some more, and so I can rewrite this in a little bit neater fashion. So I'm going to have negative I in my wire times my ratio x over 3 equals just I in my wire, since everything else canceled out, minus I in the pipe over 2. Oh, well, that's pretty simple. So I can combine my IWs if I want to, and move my IPs to the other side, and solve for what IW is, since the ratio x and the IP value are all things that we know. So I'm going to leave it here. I trust your guys' algebra skills, but that should enable you to solve for the correct solution. If you have any other questions, go ahead and let me know. Otherwise, have yourselves a box-worthy day. Hope the exam went well.